Okay, hi again. Our break is over. So let's go over the examples that we prepared for complementary slackness machinery. Here is the problem. This is the book Bahar from the book of Bahar, page 254. It's a very nice book for optimization, by the way. This is our primal problem. And you've been asked to get the optimum solution without using simplex. Okay, we can always have our good old simplex to get us a solution, but it says solve it without simplex. Now, even if it doesn't say so, by just looking at it, you could immediately see that the dual, now that you learn duality, right? The dual will have only two variables, W1 and W2, because the primal has only two constraints. So the dual can be solved by graphical solution, which is a lot easier. And then I can utilize complementary slackness conditions to find the x, optimal x, right? Because we have learned all those theorems. So let's do that. Let's take the dual, solve the dual, and then get the optimal primal solution from the optimal dual solution by the complementary slackness conditions, right? That's what it says. The dual will only have two variables, so let's take the dual. I put the primal here in case you want to follow what's going on. So I have two variables in my dual. W1 is for the first constraint, W2 is for the second constraint. Now, each variable in the primal, I'm going to have a constraint in the dual. So the dual will have 1, 2, 3, 4, 5 constraints. Each one corresponds to one variable. For the first variable, for example, W1 times 2W2 should be less than or equal to 2 because x1 is in the correct form, the constraint is in the correct form, right? If you do if you follow the duality conditions, this is actually the dual problem. Fine, it only has two variables with 5 constraints, but if you plot it, okay, this is what you're going to find out. W1 4 over 5, W3 4 over 5, and WB equals 5, your objective function value. Okay, yes, we did find out the optimal dual solution. Now let's utilize that. So let me write it here. So W1 equals 4 over 5 and W2 equals 3 over 5 is optimal for my dual, right? Now, how can I get x from there? It complementary slackness conditions. I'm sure it's here. Let's see. The first part, W times Ix bar minus B. Now, W1 is 4 over 5, W2 is 3 over 5. Both W's are not 0. That means my constraints in here should be satisfied at equality in my x vector. For the optimal x vector, all conditions, all two constraints should be binding, right? Because W1 and W2 are non-zero. This gives me this first set of lines. All right. Now, if you go on, this is first. The second part is from the dual. Well, I didn't have enough patience to write it too, but x1 times the first constraint, x2 times the second constraint for the dual, right? You write it down. The first one, my W is 4 over 5 and 3 over 5. If you put it in, it doesn't give any information. The second constraint says this is not 0. So the x2 should be 0. So I will have x1, x2, x3, x4, and x5. From here, we have found out that x2 should be equal to 0. Ugh, I keep making the same mistake. I say 0, but I write 2. I don't know why. All right. So my x2 is 0. I deduced it from the complementary slackness conditions from here. The third constraint, again, forces x3 to be 0. And the fourth constraint forces x4 to be 0. All right, I'm left with 2 x's only. And I have 2 equalities to satisfy. Remember, these guys should be satisfied at equality. So if you put it in, then I have x1, 2, 3 are 0, plus 3x5. Should be equal to 4, And the second constraint, 2x1 plus x5 should be equal to 3. You're just left with 2 by 2 equations. Solve it. Here's your x vector. x1 is 1. Everybody else is 0. x5 is 1 again. Be careful. You have to check if it is feasible or if it's feasible or not. The feasibility, you put it in here. Constraints are equality. Everybody has to be non-negative. Everybody is non-negative, so fine. We did find the optimal primal solution by utilizing complementary slackness condition of this 5-variable problem by graphical solution plus complementary slackness conditions. Any questions? Is it clear? Any questions? There was a question in the Zoom, but someone else answered it. Thank you very much. Then we're moving towards another example. Okay. Here is the next example then. You're given an LP and you're asked, and you're given an X vector, and you have been asked if it is feasible, if it is optimal or not. X2 to 0 is optimal for the following LP. Let's see. First of all, the very first thing you're supposed to do all the time is check feasibility, because you may have points here which are not necessarily feasible, and you may try to prove that they're optimal. Yeah? Very first thing, check feasibility. Put the point in the constraints and see if the point satisfies all the constraints. 2 to 0. The first constraint satisfied, the second satisfied, third satisfied. Everybody non-negative, everybody non-negative. Fine. So it is feasible. Now, is it optimal? All right. What we're going to do, we're going to utilize CS conditions to prove optimality of this point. Just to be, I may need this later on, so let me write this problem here. Maximize 2x2 minus 5x3 subject to x1 plus x3 greater than or equal to 2, 2x1 plus x2 plus 6x3 less than or equal to 6, x1 minus x2 plus 3x3 equals to 0. Everybody non-negative. All right. The dual, I'll have 3 variables in the dual. Yeah, W1, W2, W3. The dual will be a minimization problem since the primal is max. It's pretty, all the challenges are almost there. So let's take the dual together. Minimizing 2W1 plus 6W2 subject to, right? Now for X1, I have W1 plus 2W2 plus W3. X1 is in the correct form, so I will have the constraint in the correct form for minimization, which is greater than or equal to, and the objective function coefficient of x1 is 0. So the constraint comes like that. The second constraint is for x2, w2 minus w3. It's in the correct form, so I will have greater than or equal to 2. The third constraint is for x3, so w1 plus 6w2 plus 3w3 should be at least 6. What is 6? Minus 5, sorry. Okay, I'll have a minus 5 in here. Then the sign restrictions for my W's. W1 is for the first constraint. It is, well, it's already there, so I can't ask anything. It's in the reverse form, right? So W1 should be less than or equal to 0. W2 is for the second constraint. It's correct. It's for maximization, I want less than or equal to anyway. So W2 will be greater than or equal to 0. And W3 is for the third constraint, which is equality. So W3 will be free. Okay? This brings us to this dual solution. Now, the problem I'm trying to prove optimality is x bar 2 to 0. Okay. We have seen that it is feasible. Okay, it is feasible. Now, is it optimal? let's see. Let's look at the complementary slackness conditions. The first part said W times AX bar minus B should be equal to 0. Okay, let's put 2 to 0. So my X bar is 2 to 0. Okay, so W1 multiplied with the first constraint slack, which is X1 plus X3 minus 2, should be equal to 0. If I put X1 is 2, X3 is 0. So this will say that W1 multiplied with 0 equal to 0. Doesn't give me any information. The second thingy, still like that. Third constraint, like that. I don't get any information from the first part, W time AX bar minus B. All right. How about the second part? I go there. For the X's which are not 0, the dual should be satisfied at equality, right? X1 is not 0, so the first constraint should be binding, which means W1 plus 2W2 plus W3 should be equal to 0. Fine. The second constraint variable is 2, which is not 0. So I have to have the second constraint as binding, which is W2 minus W3 should be equal to 0. Third X is 0 anyway, so that doesn't give me any information. Now I need 3W. Okay, I don't fix any W's in the upper part, from the upper part, and I only have 2 conditions. So 3 variables, 2 constraints. How should I find this W? This is like then the conditions I have is, let me write them in here because I will use it later on. So I know W1 plus 2W2 plus W3 should be equal to 0. And W2 minus W3 should be equal to 2. That's all I know, right? Now, the issue here is, now, in order to declare that this guy is optimal, I have to prove that there is a dual feasible and satisfies CS with it, complementary slackness conditions with it, right? Now, I did write the complementary slackness conditions. Now, if I can find such a W, okay, be very careful because this is one of the important challenges of the implications of the complementary slackness conditions. I've given you a solution X, a point X, and I'm asking, is it optimal or not? I'm not asking you the optimal dual solution or whatever. I'm just asking, prove me that this guy is optimal, or the reverse. Prove me that it is not optimal. Yeah. Now, I take the point. If, in order to utilize CS conditions, all I need to do is, if there is a feasible W which satisfies CS conditions with this guy, I can safely say that this X bar is optimal, because that if and only if statement is pretty powerful, right? So all I need to do is find that W or prove the existence of such a W. This is important. Now, here I am left with 2 equations with 3 unknowns. If I can say that there are solutions, there is at least one solution here, I can safely say that this X bar is optimal. Yeah. So just look at this and assume that I'm just trying to see if this system of equations is solvable or not. Yeah. So from this second line, I can say W2 is actually 2 plus A, and my W3 is A. All right. If I say W3 is A, something, I don't know. All I need to do is, if such an A exists, giving me a feasible W, I can claim that my original point X star would be optimal. Yeah? Okay, let's say W3 is A. W2 then will be 2 plus A, because they should satisfy CS together. And when you put that in, my W will be, my W1 will be minus 4 minus 3A. Okay, for I did find a generic W, right? That satisfies CS conditions together with 220. Now, if this W is feasible, I would say that, yay, my primal X bar was optimal. If this W, if there is no such A, then I would say that, you know what, your starting point, there is no feasible W which satisfies CS with this guy, so this cannot be optimal. All right? That's what we're going to do. Okay. This is my dual, right? And this is the point that I'm trying to find out. Let me write the W1 also, because I will change the slide. It's -4 minus 3a. Okay. All I need to do right now is drive and see if such a feasible W exists. What do I need for it being feasible? Okay. All I need to do is utilize my complementary duality. Yeah. I know that this vector, let me put the vector in here too. My W vector is W1 is -4 minus 3a. W2 is 2 plus a. And W3 is a. Okay? Now, I know that this vector satisfies the first two conditions at equality. That's what I used. So all I need to do is check the third condition and domain constraints. The third condition is W1 plus 6W2 plus 3W3 greater than equal to -5. Okay, let's put that in. If you put them in, -4 minus 3a plus 12, 6W2 plus 3W3 should be greater than equal to -5. Well, then from here, your A, the generic A, should be greater than equal to -13 over 6. Fine. Hold it aside. Now you have to check the other W's. W1 should be less than or equal to 0. W1 is -4 minus 3a. So your -4 minus 3a should be less than or equal to 0. If you put that in, your A becomes greater than or equal to -4 over 3. Now W2 should be greater than or equal to 0. W2 is 2 plus a, so your A should be greater than or equal to -2. As you see, all these feasibility conditions actually brings me to a region for A. Fine, it exists. Because they may have overlap or they may lead to inconsistent inequalities. But in here, if my A is greater than or equal to -4 over 3, like 0, for example. If you take A equals to 0, then your vector will be -4, 2, and 0. It will satisfy it's feasible. It satisfies all the conditions of the duality. And it does satisfy the CS conditions together with my vector. So yes, then it's optimal. Interesting. The issue here is, what's happening here is, primal, I don't know if it's unique or not, primal has an optimal solution 220, and that 220 corresponds to a set of alternative optimal solutions. The dual has alternative optimal solutions. This vector W for A greater than or equal to -4 over 3 is optimal for dual. Okay? So sometimes we do come up with a W vector, the whole point, and we check its feasibility. Sometimes we need to prove that such a vector exists. If this 220 was not optimal, then these conditions would be conflicting with each other. I would easily say that, you know what, there is no such A. In that case, I could easily say that this 220 corresponds to an infeasible dual vector, so it's not optimal. Because with the complementary slackness conditions now then, each primal dual pair each primal solution has a dual pair which satisfies CS conditions with it. We just shoved it, yeah? If these guys are feasible, they're optimal. If not, I cannot utilize the theorem. Any questions? This was a tricky one, so I'll sip a glass of some water and I'll wait you to go through your thoughts. And if you have any questions, please ask. No questions? Clear? No problem, huh? Okay, then I go on. If you don't ask any questions, I'm assuming you're following what I'm doing. And I'm to my next example.
May I ask a question?
Sure, Gökçe, please do so.
In the equations that you found through complementary slackness. You have found that V1 plus 2, W1 plus 2, W2 plus W3 equals 0, and W2 minus W3 equals 2.
Yes.
So couldn't we just go this way instead? I mean, by strong duality theorem, if the given vector is optimal solution, then the optimal values for both primal and dual should be equal, right? So if we plug in the values to the objective function, then primal is 4. So with this logic, dual should be 4 too. Instead of that, couldn't we just add these two formulas together and achieve 4 like that? Because that way, W1.
The third constraint. Thank you for bringing this in. Okay, it's a very good question. You're saying that, now let me rephrase it for the ones who couldn't follow and for the recording option also. She's saying that since at optimality their objective function values should be equal anyway, why don't I use the fact that 2W1 plus 6W2, which is my objective function in the dual, should be equal to the objective function value from the primal, which is supposed to be 4. Because if you plug in this value in the primal, you're going to get 4. My answer for that is that you're utilizing corollary 1 of weak duality theorem. But be careful. Weak duality theorem can only be used if W is feasible. Okay? So you could put that in, and then you may find a W, but let's see what's going to happen if you put that in. You're going to say 2W1 plus 6W2 should be equal to 4, right? Which will bring you the third constraint. And I guess you could, follow through that. But I hope I have such an example. There are such examples where you put the objective function also, and you see that their values are equal. But keep in mind, you always have to check feasibility too. Okay? So if the values are not feasible for the respective problems, you cannot. And sometimes, I don't know if it is here too. Sometimes, even if you put the third constraint in, you do the elementary row operations and you're still stuck with 2 valid equations anyway. The objective functions equality thingy usually does not work that much. Let's if you say 2W1, my W1 is like this, so let's put it in. Minus 8 minus 6A plus 6W2. My W2 was what? So like this, plus 12 plus 6A plus nothing should be equal to 4. Well, it is 4. You see? It's not giving me any more information anyway. That happens. So because here we have, no. If primal is feasible, the dual, be careful. That's going to happen. I'll give you a feasible X. You will find you will utilize complementary slack conditions. I'm answering Oktay's question right now. I will give you a feasible X. You will utilize complementary slackness conditions and find a dual. But that dual is only feasible if the original primal was optimal. If the original problem I gave you, if the point I gave you is not optimal, you will find a dual solution that satisfies CS conditions. And their objective function values will also be equal because of the CX conditions. But it may not be feasible. The dual that you find like this may not be feasible. Only if the point I gave you was optimal, then your dual will be feasible. Okay? I hope I'll have such a question. Let's go over this one first. All right? I gave you a primal problem it says find the optimal dual solution. Okay. They're both in dimension 2, so life is easy. My primal optimal solution is 4 over 3 and 14 over 3. My dual optimal solution is 5 over 3 and 12 over 3. Okay. Now we have learned many tricks to utilize, so let's do that. Alternative 1, use strong duality theorem. It says find the optimal dual solution, right? My optimal primal solution is 4 over 3 and 14 over 3. Strong duality theorem says optimal dual is CBB inverse. Yeah? Okay. This point, x 4 over 3 and x2 14 over 3, apparently these guys are basic because they're both, well, if I make it equality, I need 2 basic variables, and they are x1 and x2. Then my B is their values, and my CBB inverse is then this. And their objective function values will definitely be equal to each other. So the first thing you could do, given a primal, let's say you don't solve the dual like this, utilize the optimal primal solution to get the optimal dual solution. Okay, the first thing you could do is use strong duality theorem. All right. Second version is CS conditions. Write the CS conditions. The first 2 doesn't give you anything, but the second 2 give you 2 equations that needs to be satisfied together, which gives you the optimal dual solution. Okay? All right. Let's come back here. I'm still at the same problem, I guess. I'm giving you a point 0.04, and I'm asking, is it optimal? Let me bring back the original problem here. It was maximizing x1 plus 3x2 subject to x1 plus x2 less than or equal to 6 minus x1 plus 2x2 less than or equal to 8, x1, x2 non-negative. My dual is minimizing 6w1 plus 8w2 subject to w1 minus w2 greater than or equal to 1, w1 plus 2w2 greater than or equal to 3, w1, w2 non-negative. Okay? Now, the question is 0.4 optimal? 0, x bar, 0.4. Okay. Is it feasible? Never ever forget this step, right? We check feasibility, 0.4, 4 less than or equal to 6, 8 less than or equal to 8. They're both non-negative, so yes, it is feasible. Let's write the complementary slackness conditions. W1 multiplied with the slack in the first constraint, x1 plus x2 minus 6 should be equal to 0. x1 plus x2 is 4, so W1 should be equal to 0. W2 times the second constraint, but the second constraint is binding at that x star, so it doesn't give me any information. The third line from here, x1 is already 0, so I can't utilize the first constraint of the dual. But I have to be sure that the second constraint is satisfied at equality. This does give me W1 equals to 0, W2 equals to 3 over 2. Okay? All right, I did find a W. Now, just for the trick of it, let's look at the objective function values. 0.4, what does it give? Cx star is 12. I did find 0, 3 over 2. What does it give me? W bar B, W0, 8 times, what's that? 8 times 3 over 2. It's again 12. Objective function values are equal. They're satisfying complementary slackness conditions. Are they optimal? No, we just saw it, right? It shouldn't be because the graphical solution, give the 0.4 is here. It cannot be optimal. What's happening here? Well, what's happening is this point is not feasible. Look, I didn't utilize the first condition of the dual. If you put it in to the first constraint, it says W1 minus W2 should be greater than or equal to 1. W1 is 0 minus 3 over 2 greater than or equal to 1. It's not. So, okay, this 0.4 feasible. has a dual solution that does satisfy complementary slackness conditions together. Interestingly, the objective function's values are also equal. But you know what? They're not optimal. Why not? Because this W is not feasible. That was the thingy that could happen, and you need to be careful about. Any questions? Any questions? Let me wait for 1 minute. Okay. I really like this. This is the last slide for duality theorems. It's a very important fact. It's a fun fact. Let's see a fun fact. What does it say? Complementary slackness is always satisfied during simplex method. Now let's remember the simplex method. What are we doing? We start with a feasible solution and we move to our neighboring feasible solutions, adjacent feasible solutions. And remember, there is the CBB inverse thingy. So interestingly, what this statement says, so there is a feasible X in my hand, and I'm always finding a dual solution, CBB inverse. Yeah? The point that we stop the simplex algorithm is when the dual became feasible. Because let me prove this statement. It's a very nice proof, actually. At each step of the simplex algorithm, for every BFS in the simplex algorithm, complementary slackness is always satisfied with the dual, which is CBB inverse. Okay? So every primal X corresponds to a dual solution which satisfies CS conditions with it, which is CBB inverse. But that dual is not necessarily optimal. It's only optimal when the primal, the X star that I have written that W4 was also optimal. Let me prove this statement. Simplex method. Then the simplex always goes with dual vectors which satisfy CS conditions but not necessarily feasible. Let me take this as my primal, equality. All right? Because simplex works with for equality. So max CX subject to AX equals to B, X non-negative. Its dual is this. The W will be free. Okay. What I'm going to prove you is at each iteration, the WCBB inverse will always satisfy CS conditions. Why? The first CS conditions is W times AX bar minus B equal to 0. Now, I did start with AX equals to B anyway. So the first part of the complementary slackness conditions are always satisfied in the simplex table because my simplex is for AX equals to B anyway. So I always have this part equal to 0. So their multiplication is always 0. All right? How about the second part of the complementary slackness, which is C minus WA times X equals to 0. Is this true? Let's see. This is simplex we're talking about. So my X is XB and XN, right? Now, the W I'm claiming is CBB inverse. Okay. So what's happening then? It says C minus CBB inverse A times X equals to 0. That's what I'm trying to prove, right? Now be careful. For XB, this is my row 0. Remember? Let me find you that. Somewhere here. There it is. You see our table? CBB inverse A minus C is my rho zero coefficient, actually. Yeah, CBB inverse A minus C. Now, what's happening in the simplex then? I'm always satisfying, because for basic variables, this is my rho zero coefficient. Yeah? So if X is XB, then X is not zero, but its multiplier is zero, rho zero coefficient. Well, for X equals Xn, these guys are already zero. I don't care what's happening there. Yeah? So that's what it says. If Xi is zero, it is not zero, then it's a basic variable and its rho zero coefficient is zero. If Xi is zero, I don't care what the multiplier is. The condition is always satisfied. So this is an interesting fun fact. Simplex method always satisfies, well, the X and its corresponding CBB inverse W vector always satisfies complementary slackness conditions. When do we stop? We stop when all rho zero is non-negative, which is actually the dual feasibility. Okay? So at the simplex iteration, we have primal feasibility on our hand, and we always satisfy complementary slackness conditions. We stop when we find the W vector CBB inverse, which is feasible. Remember the proof of strong duality theorem? We proved that CBB inverse is actually, the rho zero being non-negative was actually our dual feasibility anyway. And we were saying that primal feasible, dual feasible, objective functions are equal. For corollary 1, I can declare that these guys are optimal. Well, you can prove the same thing with complementary slackness conditions now. Primal feasible, complementary slackness are satisfied. Well, if the dual is feasible, we are optimal. Okay? So all these theorems are somehow linked to each other. They're always yielding to the fact that, well, if they have to be feasible, then there are certain conditions that we derived, and based on that, we could prove optimality. Any questions? Okay, then. I have covered all the material required for the homework that you currently have, for the study sets that we have assigned, which means for the practice sessions next week and for the quiz next Saturday. We have already scheduled it via exam scheduling, so you should be able to see that. Let me stop recording because I'm done with course materials.